also known as conducting arteries. They would include the aorta and some of the major branches close to the aorta, like the common carotids that go up into your neck.
Do you have any extras?
Look in the box down there on the floor. And then as we move off of the aorta and into the organs, we lose those elastic sheets, and these are identified as muscular arteries, even though the elastic arteries obviously have muscle. And these are also identified as distributing arteries. Pardon?
After the aorta?
Yeah, well, branches off of the aorta are farther branches. Yeah. So, distributing arteries. All right, so if you think of a major freeway, like I-5 as the elastic arteries, and major streets off of that as also elastic arteries, and then you get onto the surface streets, those would be distributing arteries. Okay, so College Oak, Madison, right where it comes onto or off of 80 would be an elastic artery, but where it crosses Sunrise, by that time would be a distributing artery. Okay, so the farther we move away from the heart, the fewer elastic fibers we have, and the more we move into a muscular artery. So this is not just a sudden, you're either this or that. Sometimes there's going to be some slight changes. Yes?
Is there a general pressure in correlation to when it's
Probably, but I don't know what it is, because certainly distance is affected by pressure. Okay? You don't need to, I'm not going to ask you to identify an artery as an elastic artery or a muscular artery. I just want you to know what the characteristics are. Okay? And then we just have our muscular arteries are going to just decrease in size and get smaller and smaller and smaller and smaller. And they're defined by certain diameters. The next structure we're going to look at characteristically is known as an arteriole. And by definition, I'll describe this as having no more than 2 layers of smooth muscle in its wall. Okay. Arterioles represent the vessel's most important in regulating blood pressure. There are many of them, and they still have enough smooth muscle. Their surface area is greater. So I'll go over that when we get to arterioles a little bit better, why they do that. And then as we lose the smooth muscle from arterioles, we have capillaries. Capillaries have the smallest diameter. They also are the most numerous. So as we're looking at our pathway here, we have the arterial flow pressure in the muscular arteries is going to be greater than pressure in the arterioles, which is going to be greater than pressure in the capillaries. Now as we move from capillaries rejoin to form venules. So is pressure going to be greater in a venule or a capillary? Good. So even though we're rejoining and forming larger vessels, the pressure is still dropping. Because pressure has to drop subsequent to each of these steps in order for blood to return to the heart.
That actually makes sense because you're getting larger on that side.
So venules and then veins. And we have various size veins. And then of course we have our large vena cavas. Superior and inferior vena cavas. Now let's look at the characteristic wall component of our blood vessels. And until we get to capillaries, on both sides, arteries or veins have the same 3 types of layers. Remember we had 3 layers of the heart wall? We have 3 layers of a blood vessel wall. Okay. So the 3 layers are identified as the 3 tunics. The lining is known as the tunica intima. That would be homologous to what layer of the heart wall? Tunica, well, either endocardium, okay? And then our smooth muscle layer is known as the tunica media, and that would be equivalent to the myocardium of the heart, which is cardiac muscle. This is going to be smooth muscle. And then we have the tunica externa, which you may also see identified as the tunica adventitia.
And this is for arterioles and veins?
Yes, arteries and veins, including arterioles. Now, typically, just as a real general characteristic, the key difference in thickness between the artery and vein is due to the amount of muscle. And so it's primarily the tunica media that is going to be different when we compare a wall structure for an artery or a wall structure for a vein. And that reflects the pressure resistance that's occurring across those vessels. So if you look at the lumen, let's say that we have the lumen of an artery, and we have the lumen of a vein of nearly identical diameters. The amount of smooth muscle that would be present in the artery versus in the vein would be about like that. Okay, so about a third of the amount of muscle in the artery is required to resist the pressure as we have for the vein. And there'll be a few other, the orientation of the smooth muscle is a little bit different. So here's another view. This is a muscular artery. You can tell because of the presence of a sheet of elastic fibers right at the tunica intima that are associated with that and throwing it into deep folds. You can see that in our tissue slides, the arteries tend to maintain their opening, whereas veins collapse. And again, that has to do with the amount of smooth muscle present. So here's another image of the layers. We have something similar here. This is one of our newer models. Jeff loves to go shopping. And since Jeff took Bio 430, and Jeff is the guy that runs our open labs, took 430 and 431 from me. He's biased towards what I want, so I get to feed him. Hey, I want this model. So this shows the structure from outside to inside of an artery and a vein. And then the vein is cut open here so you can see the valve structures. Okay? On the back, it's showing the effect of muscle contraction on veins. We'll talk about that in a bit. So now let's take these vessels, and I'll diagram on the board and identify the tissue characteristics that we see with the three different components of the vessel wall and why it contributes to that particular function. So the first one we'll look at are the elastic arteries. And the tunica intima of elastic arteries is formed of tissue very similar to the endocardium, though not as thick. We're going to have a simple squamous epithelium. My diagrams are not going to be proportional to size because you wouldn't be able to see the capillary, or I'd have to draw a really huge elastic artery so you would be able to see the capillary. So again, it's not going to be proportional. But we have a lining epithelium, which is simple squamous. And underneath every epithelium is what type of connective tissue? Loose irregular. So that's our standard tunica intima for all of our vessels. Okay. Then we add the tunica media. And obviously, since we're talking about an artery, we're going to have a thick amount of smooth muscle. And the smooth muscle cells are oriented so that they are found in their longitudinal orientation around. So we're not cutting, when we cut a blood vessel in cross section, we're cutting the smooth muscle cell in its longitudinal section. And here, where we're cutting the blood vessel in longitudinal section, the smooth muscle cells are cut in cross section. All right, so if you were to look at a blood vessel, and we'll see this with the arterial, if you were to look at a blood vessel in longitudinal section, cutting the length of the vessel, you're going to see the smooth muscle cells, small and large circles, because the smooth muscle cell is fusiform in shape. So if we cut here, it's going to create a small circle, and if we cut here, it's going to create a large circle. So when you look at a longitudinal cut of a blood vessel, you're going to see the cells, the smooth muscle cells, cut in cross section. You look at a cross section of a blood vessel, you're going to see the cells cut longitudinally. Okay? So rather than draw every cell, I'm just going to do this. We have a thick layer of smooth muscle cells. In an elastic artery, we also have sheets of elastic fibers. Elastic fibers need to be stained with a silver stain to be seen, so they are black. And you can see this staining on your lecture notes. There's a photograph. Even in black and white, you can see the dark lines of the stained elastic fibers. No, go back. You want to go back. Those are PowerPoint slides, your lecture notes. Go page 74 of your lecture notes. So the purpose of this elastic, since these vessels are under such high pressure so close to the heart, is not so much for the expansion as to help them recoil as that blood is helping it to move on. So elastic has a return to normal length factor. All right, yes, it can stretch, and we often tend to think of the elastic stretching capability, and we forget about its recoil. And it's that recoil component that is important. So if we look at an elastic band, a rubber band, and you think of that as the elastic fibers around the blood vessel wall, and as the heart pumps blood into the aorta, it stretches it, and then as that blood comes back, that elastic recoil helps to compress the blood and continue to move it through. Okay? So that's its importance here. All right, now let's look at muscular arteries. So I'm going to leave up most of this. I'm going to erase the elastic fiber sheets. Tunica, let me put the tunica externa up here first. Tunica externa in this large vessel is going to be dense, irregular connective tissue, forming a thin capsule that helps to hold everything in place and anchor the blood vessel in the muscle or along the chest wall, wherever it is.
Helps to enter blood vessels
to its surrounding tissue. So now we're looking at muscular arteries, which are most of the arteries in the body, are going to be muscular arteries. And back to this previous image, which was of a muscular artery. Notice how ruffled the lining of the muscular artery appears to be. And if you have these slides, On PowerPoint, you can see there's a dark purple line, just deep to the epithelium. So we make those changes between elastic and conducting arteries.